calculate the Joule's coefficient and Joule-Thomson coefficient for van der Waals gas. We have done that for Joule coefficient for van der Waals gas, right. Now, let us do for Joule-Thomson coefficient. So, again P equal to R T by V minus B minus A by V square. This is our starting point, and we need to calculate del H by del P at a constant temperature. In fact, if I have to calculate the Joule Thomson coefficient, I have to divide by minus 1 by C P. Okay. So, that means we have to redo the whole thing back again, right. So, and I do not have the marking with me right now, but we are going to, I have to do that quickly. So, I will just do that once more. So, we have to calculate del H by, no, just change this color, del H by del P at a constant temperature. This is what we are going to calculate, right. So, H is, I am going to do it a little bit faster now. So, am I doing it correctly till now? So, I have got equation number 1, in which I have this, and then I have equation number 2, which I have to put in equation number 1. So, without doing any this thing, I will just put that. So, del U by del V T del V by del P T plus del U by del T V del T by del P T, that is just this one, plus P del V by del P T plus V. Can I take anything common? Del V by del P I can take common. So, del U by del V T and del V by del P I can take common. Oh, so plus P plus C V is it going in the right direction? So, let me see whether we are doing it rightly or not. So, U plus P V, so del U by del P T plus P del V by del P T plus V, this is correct. And now we are coming here, and then we write this del U by del V by del P, del U by del T by del P T, correct. Now, when I write that, we del U by del V T del V by del P T, that is correct, that is correct. Okay. So, now del V by del P I have taken common, that is also fine, and del U by del V T plus P, that is fine, V I have, and del U by del T V C V, I think it is fine. Okay. Now, we have to evaluate this. So, it just looks big, but you see in the derivation there was no ambiguity, that is the most important thing. We can make it bigger or whatever, but there should not be any ambiguity. Now, as I said that in order to write del U by del V, we used a trick, right. That trick we have to use again. Let me erase this part very carefully. Only thing is that we do not want to remember anything, we want to do it from scratch. So, this is our final expression. So, I can just remove this line also. Now, del u by del v t can be written as t del p by del t v minus p, again which you will learn later. Now, this equation 1, now I am denoting that equation 1 and equation 2. So, I am going to put equation 2 in equation 1 and derive it again, del h by del p t. I am going to put equation 2 in equation 1. So, I am going to write t del p del t v minus p here. So, plus, so I am replacing the whole thing here into this plus del v del t p del p t plus C v del t del p t plus v. Now, one thing cancels p, that is a good thing. Now, giving us t del p del t v del v del p t plus C v del t del p. Oh, so why I was writing all that all along? This quantity is 0 plus v. You see, that was I was just writing for because I did not notice that it was at a constant temperature. You understand? So, so now I have the this thing. So, I am going to delete this portion now. I am now more or less handle on the situation. Now, it is giving me this quantity t del p del t v del v del p t plus v. Now, nice looking small expression. Now, we are going to go back and derive this quantity for ideal gas for van der Waals gas situation, and we know how to do that now. P equal to R T by V minus B minus A by V square. So, I am going to take derivative with respect to T now at a constant volume, which means I am going to get R by V minus B, this quantity. Now, del V del P will is not going to be so easy. So, if I want to do del V del P, how do I write it? We have to take the derivative of V with respect to P. We can take P with V and then invert it. Okay. So, we can say del P del V at a constant T is R T minus R T by V minus B square minus 2A by V cube. Am I correct? Which is giving me minus R T by V minus B square plus 2A by V cube. You see, it is del P del V, we need just the opposite of that. So, an inverse of that, right. In that case, of course, we can invert that and you can put it and get the expression, but let us take a simpler situation in which A is going to be 0. What does it mean? That particles do not have any interactions among them. All that it has is that it has a finite size. That means, it cannot really go and bump into each other. So, we are taking a limiting case of A is 0 and B has a finite volume. Remember, if B is also 0, we are going to go to the ideal gas. Okay. But if B is non-zero, then it is not fully ideal gas, although the interaction is 0, but it is not. Actually, in that case, the potential is up to B it is 0, at B it is infinity. Okay. So, now if you do that, our life becomes simpler and we can get this quantity. So, let us write that for A equal to 0 case, del H by del P t is T into R by V minus B multiplied by V minus B square by minus R T. You see what I did? I just took invert of that. I took A equal to 0, which gave me only this quantity, and since it is del P del V T, I just inverted it. Did you get, did you follow this particular part? Now what I am going to do is that my R T cancels each other, V minus B cancels each other, and but there is a negative sign. So, and plus V. So, what I am going to get? So, this V is basically molar volume always everywhere. So, minus V minus B plus V, which is minus V plus B plus V, giving you B. So, in case A is 0, see if A is non-zero, then you should do this particular part. What you are going to do is that, you have to simply do this particular algebra, this part, and then invert it and put there, and you will get an expression. But interesting thing that I am going to show you here is that the Joule-Thomson coefficient mu j t is 1 by C p del H by del P t, right. What is Joule-Thomson coefficient? We know del T by del P at a constant H, that was Joule-Thomson coefficient, right, minus 1 by C p into B, where in the Van der Waals gas case where A equal to 0, in V d W gas. Now, B is a positive quantity, C p is a positive quantity. What does it mean? When the pressure increases, temperature decreases. When the pressure decreases, temperature increases. So, instead of becoming cooler, it gets hotter. So, therefore, Joule-Thomson coefficient is not always giving you. So, in this particular case, Joule-Thomson coefficient is a negative quantity. So, Joule-Thomson coefficient is not always going to give you a decrease. That is what the interesting point about this particular thing, that here temperature increases for decrease in pressure in this particular case. Okay. So, we have calculated that. So, I am going to just delete this part, and I do not have, okay, I have the expression, right. So, I will just write it down. So, del T by del P at a constant H is going to be minus B by C p for A equal to 0 in V d W gas. Now, why is that the case? Because here the B parameter prevents the particle from going into each other. It is a repulsive type of interaction. Okay. So, it turns out that wherever there is a repulsive type of interaction, you are going to get a negative Joule-Thomson value, such that it will get heated up rather than getting cooled down. But if you had an attractive term, for example, if you had that A term, you would see that it will actually cool down, and it is given by this kind of diagram, in which you can see that wherever there is mu less than 0, you are having heating instead of cooling, and wherever there is mu greater than 0, it is there is a cooling. So, for a real gas system, A is not 0 for a real gas does have interaction. So, in real gas situation, you are going to get a cooling effect. Typically, it is used for cooling, but that cooling is limited to a given range of temperature and a given range of pressure. If you are in this region, this particular shaded region, then there will be a cooling effect. However, if you are in this particular region, there will be a heating effect. So, the cooling effect, which corresponds to mu greater than 0, is observed under the condition when attractive interactions are dominant, because the molecules have to climb apart against the attractive force, as I told you the situation for Joule's coefficient also. For molecules under condition where repulsive interactions are dominant, repulsions are dominant, Joule-Thomson effect results in gas becoming warmer or mu less than 0, and we have shown you one example how the mu becomes negative when attractive interactions are not there and you have only B. And you know, so having B means, again as I told you, having B means your potential is 0, your potential is 0 everywhere, actually your potential is 0 everywhere except, so this is the distance, okay. Your potential is 0 till everywhere except below B and below, where it is infinity. It is called hard sphere potential. It cannot get B or below the value, that is the volume occupied by the particle. So, it is a repulsive interaction. So, I just shown you that anything below this value will be below, and at the value B it will be infinity. Okay. So, and we see that is the repulsive potential, right, at the value of B, and that is preventing, that is giving us a heating effect.